Hello viewers and my dear students. Welcome to the new chapter analysis of Axisymmetric Solids. I'll give you a demo on analysis of a closed cylinder under pressure using Ansys Release 14. These are all offline video help files prepared by me, Dr. B. Gurudat, former professor and head, Department of Mechanical Engineering, Bangalore Institute of Technology, Care Road, Bangalore 4, presently working as professor at the Department of Mechanical Engineering, Nittai Meenakshi Institute of Technology, Yelahanka, Bangalore 64. Okay, now in this problem, actually if you see, this is a closed cylinder, you understand. This is a closed cylinder under pressure. Okay, this is a closed cylinder. That means this length is 24, this length is 20, this is 10, this is 6.8 in that way. And you have a space here. This is subjected to fluid under pressure. Okay, as you see here, this is the thickness of the cylinder and you have internal pressure here. Okay, as you see here, this is 100 mm in 10 centimeter, 100 mm. This is 68 mm means this is almost 16 mm thickness you have here. And this is 240 mm, this is 200 means this is 20 mm thickness here. Anyway, I'll give you the dimensions and all that. But here it is axis symmetry means for this problem, this is the axis. Axis symmetry means about this axis, we'll do one half. That is either the top half or bottom half is taken into consideration. Okay. Now because of this pressure, okay, see here, because of this pressure, this diameter is going to increase. Okay, please understand, these are all the concepts. Because of this pressure, this diameter, internal diameter is going to increase and the circumferential stresses will develop. Okay, the circumferential stresses, naturally they are tensile in nature and these circumferential stresses are called as hoop stresses. The hoop stresses are maximum here. Okay, when compared to hoop stresses at the outer radius. Okay, this is inner radius, this is outer radius. This you should know. That is because of the internal pressure, the diameter is going to increase. This diameter is going to increase. As a result, that every fiber here is going to expand. That means that tensile stresses are developed here. That means the diameter is going to increase here. This diameter is going to increase. As a result, in this part of the cylinder, the tensile stresses are developed. They are called as hoop stresses. Hoop stresses are developed. They are called circumferential because on the circumference you have, and that is the circumferential stresses or hoop stresses we say. And the hoop stresses are maximum here, and comparatively at the outer cylinder it will be comparatively less. Okay. Now this is, you see here, the same thing. How I model it, I have given here. Okay. How I model it, I have given here. See here, this is 240 mm. Correct now? This is 240 mm and this is 50 mm, this is 20 mm, this is 20 mm and this is 16 mm and all that. You take it from my previous slide. This I have taken. That is axis of symmetry is this. That is, that's axis of symmetry along the circumference I will take. That means one half of the circumference I have taken, other half is here. This is the axis of symmetry. Now what I will do is for modeling, I'll consider A, B, C, D, E, F, G, H and all that and H, A. In that way, A, B, C, D, E, F, G, H, A. I'll create points and I'll convert that into area. That also you can do. Otherwise, you convert this area, you make this area and again make this area and make this area, unite all the areas. That is Boolean add areas. In that way also you can do. Now I am showing you a different option where I am creating key points and making directly the areas. Okay. Now as you see here, as you see in the next slide, what you should know here is axisymmetric solids are also called as solids of revolution due to symmetry about circumference, because as you see here, the symmetry about the circumference are made. One half of the circumference is this. Okay, when you see from the top, it is a circle here. This is a circle. This is a half the circumference. Okay. Okay. That is why what you should know here is axisymmetric solids are also called as solids of revolution. Due to symmetry about circumference, the displacements are confined to radial and axial directions. Axisymmetric problems involves an additional Hooke strain due to radial displacement, giving rise to Hooke or circumferential stress. Okay, this is what you should know. Okay, now as you know here, okay, here, now here's here. Now the internal pressure, if it is developed here, this diameter, if this is the cylinder, if the internal pressure, if it increases, the diameter is going to increase. When the diameter is going to increase, in this part of the circumference, no, the tensile stresses are developed. These are all called Hooke stresses. Okay, when compared to outer, here since the pressures are here, pressure is here, here the Hooke stresses are maximum. This you have to find out. In any axisymmetric problems, Hooke stresses, that is these stresses, these are circumferential stresses, circumferential stress here, circumferential stress here, these are all very important. And then the longitudinal stress, that is along the axis. These things are very important. That's what I given. Circumferential stress or Hooke stress, a normal stress in the tangential direction. Any internal pressure applied to the cylindrical pipe will ultimately give rise to Hooke stresses. As I just now said, if there is a pressure here, this diameter is going to increase. Okay, as a result, in this, that stresses are developed. The stresses developed are called as the Hooke stresses. That is what I have told you. Okay, Hooke stresses, this is directed along the tangent to the circumference and tensile in nature. That thus there will be increase in diameter. That's what I have told you. If the pressure is there, there will be increase in diameter here. As a result, along the circumference here, there are circumferential stresses are developed, and that is called Hooke stresses. Okay, this is what, and longitudinal stress. This stress is directed along the length of the cylinder. This is also tensile in nature and tends to increase the length because of the axial stress. Because of the axial stress, the stress is directed along the length of the cylinder. This is tensile in nature and tends to increase the length of the cylinder itself to some extent depending on the pressure. Okay, these are all the things what you should know. These are all the basic things I am telling you. Okay, see here, axial stress, a normal stress parallel to the axis of cylindrical symmetry, circumferential stress or Hooke stress, a normal stress in the tangential direction. You see here, this is a Hooke stress, a tangential stress. Okay, this is axial stress, and this is what we concentrate. Hooke stress and longitudinal stress are the must. You must find in axisymmetry problems. Hooke stress and longitudinal stress you must find out. I have found out by some theoretical methods also, and will verify using Ansys also. Okay. Here, now you should know pressure cylinders and spheres which are used to store liquid, gases, compressed air, etc. are known as pressure vessels. These pressure vessels store liquid or gas, etc. at high pressure and also at high temperature condition. Pressure vessels are classified into two groups. Thin cylinders where R by T greater than 10. That means when T is very small, the thickness of the cylinder is very small, R by T will be greater than 10. When thickness is more, R by T is less than or equal to 10. If R by T is greater than 10, it is called thin cylinders. If R by T is less than or equal to 10, it is called thick cylinders. Okay. Now in this case, what we are doing is, in this our case, ours is R by T is lesser than or equal to 10. Because as you know, R is 50. You see here, in this case, you see here, R is 50. This is this R no. This is R by T. R is this 34. 34 by T is 16. That is 34 by 16 is less than that is almost 34 by 16. No, this is R internal radius, and 34 by 16 is like some 2.1, 2.2 in that way. It is definitely less than or equal to 10. As a result, this comes under thick cylinder category. Okay. Now for that, we'll have some verification done. Verification using theoretical methods we do. Since R by T less than or equal to 10, that is you are getting some 2.2, some 2.3 R by T. In that way, we consider the thick cylinder formula. This problem is brought under thick cylinder category. Here Ri is 34. R0 is 50. You see here, Ri is 34. This is totally 50 now. Ri is 34. R internal. R outer is 34 plus 16. In that way, it is 50. Okay. Ri is 34. R0 is 50. And internal pressure P is 1 Newton per millimeter square. We have the following equations for thick cylinders for getting hoop stresses or tangential stresses or circumferential stresses. P is equal to minus A plus B by x square. At inner radius, that is, at inner radius, P equal to 1. Correct? No? 1. Minus A plus B by x is 34 square. That is equation 1. At outer radius, P is equal to 0. That is, there is no pressure on the outer. It is only at the inner radius. P equal to 0. 0 is equal to minus A plus, at the outer radius, R is 50 square. That means you have two equations, equation 1 and equation 2. Subtract these two, 1 by 2. In that way, you are getting, you can solve for A and B. A you get it as 0.86. B is equal to 2150.2. The equation for hoop stress is A plus B by x square. Hoop stress at the inner radius 34 is A and B you already found out constants, and in place of x you put 34. Okay, 0.86 plus 2150.2 divided by 34, 2.72 MPa you should get. Hoop stress at the outer radius, okay, you should get it for, that is 50 mm. That is same thing, A and B same, 0.86 plus 2150.2 divided by 50 square, that is 1.72 MPa you should get. Okay, that means you should finally prove this 2.72 MPa and this that is at inner radius 2.72 MPa is hoop stress and outer radius 1.72 MPa. You should theoretical, that is you should verify using Ansys. Now I have done some basic theoretical calculations to find out the hoop stress at the inner radius and the outer radius. Okay. Now also you know, if it is a thin cylinder, it's just a matter of information. Now it is not a thin cylinder, it is a thick cylinder. Now if it is a thin cylinder, so circumferential stress is PD by 2T. Okay, circumferential stress, this circumferential stress, tangential stress. Okay, PD by 2T. And if it is longitudinal stress, it is PD by 4T and all that. These things you have to know. Now I'll give you a simple example. You see here, this is just a simple thing what you are supposed to know. This is one thing what is asked in so many interviews and all that. See here, this is a cast iron pillar. Okay, this is a bridge. Okay, pillar which is supporting this bridge. That is the road which is above this is supported by this pillar. Okay, this is a cast iron pillar of railway bridge. It is pin jointed by wrought iron hoops. These are all called hoops. Can you understand? This and all that. These are all belt like thing. These are all pin jointed hoops, stronger in tension than cast iron. That is, it is stronger than this cast iron pillar. These hoops are stronger than this cast iron pillar. Okay, cast iron pillar of railway bridge, pin jointed wrought iron hoops. These are all wrought iron hoops, stronger in tension. That is why once you do this, if there is a load on the bridge because of the trains going over that, okay, the diameter is going to increase because of the this straps what you have provided. They are called as the hoops here. This will prevent the expansion, and as a result, it prevents the cracking of this pillar. That is why the hoops, you keep it at regular places, you fix it at regular places so that the diametrical expansion is prevented. These are all the basic things what you are supposed to know in this axisymmetric problems and all that. Okay, now this is session 1. This is session 1 on axisymmetric solids. In session 2, we'll try to start with verification of this problem using Ansys. Thank you friends. Thank you for watching. Thanks again. Thank you.